we have to finish up this problem. Okay, this one was like a little bit different case scenario that asked us for the mean absolute deviation. So absolute meaning we only want the positive distance away from the mean. So that's what we found here. And then we have to actually calculate the mean of this, so the average. So our third step here, we're almost done, is we got to calculate the mean of the distances from our mean, which we've already found in red right here. Calculate the mean of the distances. Okay. So I'll start with my first one here. The deviation from 15 was 4 plus 6 plus 4 plus 3 plus 1 plus 2. So again, adding up all these. And then divide by, to averages, 6. All right, so you do get a decimal, and I believe in ALEKS they always have you round to 2 decimal places. So we'll do that here. All right, so there's an example of mean absolute standard deviation. Now today, we've been talking about all of these like measures of variation, variability, range. We're actually get to calculate some standard deviation. Variance, talk about variance too. All right, so population standard deviation is basically when you find the standard deviation, which is like the average distance the data entries are away from the mean of just of the entire population. Okay, so there's population standard deviation and sample. I think I gave the example yesterday that if you wanted to sample every single senior at FHS, that'd be an example of a population. And if you just randomly picked a sample, obviously, and did those calculations, that'd be sample deviation. So here's like the formula, and it looks scarier than it is. And I don't really use the formula. I kind of just like go through the steps of like, okay, well, I got to figure out what the mean is, and then figure out how far away it is, and then just find the average. Okay, so we use this sigma to represent standard deviation. So variance was that sigma squared. And then we talked about how standard deviation is just the square root of variance. Okay, so that's still sigma. So we take that big long equation for variance, which is the sum of the data entries minus their distance from the mean squared. Remember when we did that? Divided it by our number of entries. We used capital N to represent population. So to find the standard deviation, we just square root that variance number. And I kind of explained, like, variance doesn't have really a numerical meaning to it. It's just kind of like a middle step into helping us find standard deviation. So another thing, I mean, you can do just the square root of variance if you want. And those symbols all mean the same thing that we talked about yesterday. I'm just going to flip back to that one really quick, to this. So that sigma still means sum of all the deviations squared divided by the number of entries. So to calculate the standard deviation, we take the square root of that. That's how we calculate standard deviation. It is different, I do want to point out right away, when we calculate standard deviation of a population, it's a different formula or a different way we do it than just a sample. Okay, and the reason why, I'll kind of explain it more when we get to a sample, but because when we sample, there's like a little bit of bias. So we just have to do like a little manipulation with my number of entries here to make it like a little less bias. All right, so here's basically like the step-by-step of how you want to find standard deviation of a population. So like I said, I don't really think of this big long formula. I kind of think of it as like, hey, I know what the standard deviation is. Here's how I get there. I got to find the mean, then find the deviation, find how far away they are, and then I square those and add them all up to divide by my number. That gives me my variance. And now adding in this final step, we'll just square root it, and that number right there is your standard deviation. It is your average distance away from the mean. That's what standard deviation is. When you were, just out of curiosity, when you guys like took chem, like did you have to actually calculate standard deviation? Do you know, wasn't that? No. You just talked about what it was.
I don't really know if we talked about it at all.
Oh, well, didn't we tell you yesterday?
Psychology.
Oh, psychology, sorry. Psychology.
We didn't have to
Probably didn't have to do the math. Just talk about what it is. Okay, that makes more sense. Okay, yay! So there's something new for you. Okay. Austin's like, can't wait. So again, go back to this. When you're trying to find, again, population though, this is population. Sample we'll do a little bit later. Population, we're going to start by finding the mean of the population set. So the mean, we'd add them all up. You. Divide it by, okay, I guess I should read the problems here. These are 6 members of the family work and these are their hourly wages. Okay, so divide this by my 6 members. The mean is 18. So that's their average hourly wage in dollars. And it says, assuming that these wages constitute an entire population, find the standard deviation of the population. So this is an example of a population because we're surveying all 6 members of their family. Okay, so after I find the mean, I have to find how far each of these are from the mean, square those, and add them all together. So I kind of just do the variance like all in one step. Instead of doing like, oh, now I'm going to do 32 minus 18. Oh, now I'm going to square that number. Oh, now I'm going to add them all up. I kind of just do it in one step, and I call it my variance. So I'll kind of like walk you through. First, you got to figure out how far it deviates from the mean. So if I'm starting with 32, and I just kind of go work left to right. 32 minus my mean, 18. So there's a deviation. That's how far away it is. And then I have to square each deviation. Okay, so I'm kind of like right here. I squared each deviation, and then I have to add those all up. So at the same time, when I go to do my next one, I'm going to add these all up. And this is the same as calculating the variance. All right, so my next data entry is 15 minus, where it is from the mean, 18. There's my deviation. Square that. Next one, 12 minus 18. 21 minus 18. Bless you. 18 minus 18. Now, this makes sense. If my data point, or one of my data entries is right on the mean, obviously it doesn't deviate at all, so that's going to give us 0. I'm just going to scoot over because I just kind of ran out of them. There we go. Last one, 10 minus 18. Okay, now all we have left to do to really figure out our variance here is divide by n. You're looking at this. Divide by n, which means your number of people in the populations. So we're going to divide this by 6. And this number right here is the variance. So what I do is I type this whole thing in my calculator, like with parentheses, honestly. I just type this all in one. And you can practice this, and obviously you'll get some practice when you do this on your ALEKS assignment. But I got 314. And then I just finished by dividing that by 6. I'm not even going to simplify that fraction at all because that's not my answer. This is just my variance. So the only thing left I have to do, so right now I have my variance. That's what this symbol means. Sum those all up, divide by the number of members of my family. Now I just have to find the square root of that to get the standard deviation. So to get the standard deviation, you obviously just square root the variance. So then I just square root that number. You can simplify it if you want, but your final answer is the square root. We'll round this one to 2 decimal places as well. So that number tells you, on average, each of those wages are around $7 away from the mean. That's what that number tells you statistically. On average, now obviously there's some that are more, like 10 is obviously further away from the mean than the average, but that's the average of the distance away from 18, the mean. Okay, that's not too bad, right? I'm starting to like this because it's more mathy. Now let's look at just a sample one and how it's different. So that one again was a population. So you do have to kind of be on the lookout for, are we calculating the standard deviation of a population or just a sample? So here's how the formula is different. And they use different symbols too, which makes it confusing, but that's how they differentiate between the sample and the population. And we'll fill in these symbols in a second here in this chart. So for variance, for a sample, instead of using the sigma, we use a lowercase s squared. So it's still the sum of all the deviations squared. So the deviations are the data points and how far they are away from the mean. And they use x bar for the mean in this one instead of mu. Okay, that's squared. So that's still the sum of deviations squared. Here's the difference. We actually divide it by not my number of entries, but our number of entries minus 1. And it took me a long time to figure out kind of why. And I guess the best way it was explained to me, it's if you divide by your actual numbers of the population, it just doesn't make your statistic as reliable, or it's a little biased. You kind of have to subtract 1, and it just makes it a little bit more accurate, I guess. They just said if you just divide by your number, it makes it biased. So that's the only difference with these formulas, is this is actually the number of n in your population, n in your sample, not population. Let's do entries minus 1. So then the standard deviation is still the square root of that. So we just take the square root of that variance. You can still, if you want to, this is the mean, if you want to write those. It's up to you. This still means sum. Okay. So standard deviation. Same thing with the n minus 1 if we're talking about a population. Oh, gosh, I keep saying that wrong. Sorry. If we're talking about a sample. These ones are sample. We'll try one in a second, but first let's fill in these symbols then, because it is kind of confusing. They use different symbols depending on if we're calculating statistics for a population or just a sample. Okay, so for variance, if we're talking about a population, that's sigma squared. A sample is just a lowercase s squared. So standard deviation, since it's just the square root of variance, for a population it's just sigma or just s in the sample. For mean, we use mu when we're talking about a population, x bar when we're talking about a sample. The only reason I don't know why they specifically use each for this, why is this in the population? I would just say they obviously have to have 2 different ones because it is different calculating standard deviation of population versus just a sample. Number of entries, they use a capital N for population, lowercase n for sample. So deviation, that's how far your data entry is from your mean. So it's obviously just going to use mu for a population and x bar for a sample. And then the sum of squares, so that just means adding up all those deviations squared. So again, obviously you're just going to use mu when we're talking about a population, and x bar when we're talking about a sample. Okay. So I screenshotted this again from your book of just like kind of the step-by-step. I do like how it's like laid out how to calculate sample variance and standard deviation. So folks, the only thing that's different is we just have to remember to minus 1 when we divide by our total number of entries in the sample. That's the only thing that's different. If you want to highlight it, you can. But it's the same like steps. Okay, so let's try a sample one. So notice in this question, it says below are the times and days it takes for a sample of 6 customers from Justin's computer store to pay their invoices. Find the standard deviation of this sample of times. Round your answer to 2 decimal places. All right, so first step, we're going to calculate the mean. And again, I'm going to use the X bar. I'm using the correct symbols. We're talking about samples. So the mean, add up all the numbers. Now to calculate the mean, I'm still going to divide by 6. Just when I get to that variance. So the mean here is 30. So on average, 30, wait, the time and days it takes, to pay their invoices. Oh, that's funny. On average, it takes them 30 days. That's a long time. Next, we're going to find those deviations, and we're going to add them all up. And we're technically finding our variance. So this is S squared. Okay, so I start by just going through each data point. First, calculate the variation, the deviation. So 21 minus, how far is that away from my mean? Okay, I'm going to square it and keep adding these up as we go. 26 minus 30 squared, 43 minus 30 squared plus 34 minus 30 squared. Last one. Make sure when you're typing this in your calculator, you're like using the parentheses. All right, now here's a big difference. Here's the big warning. We divide this by 6 minus 1. We divide this by 5. I'm going to highlight this. It's a big difference because we do a sample. That's the only difference. Okay. So like I said, be careful typing this in your calculator. Type that all in. We get 628 divided by 5. I just keep it like that because my last step to calculate the standard deviation, I just square root that number. And then I just type that in my calculator. Are we good with typing like fractions in the calculator? Okay. Because for some reason my geometry kids can just not figure it out. So on average, the entries differ from the mean about 11.21 days. Which makes sense because we have a pretty wide range here. 30 is right in the middle, but I have one that's as low as 15. I have one that's as high as 43. Like that's a pretty big spread. And that's one thing that standard deviation is measuring is like our variance, how spread out the data is. Ooh, histogram. So the only thing that's different with like a histogram is remember this is plotting like your frequency. Okay? So you're not actually sure. Like if we were to read through this, many tests that purport to measure intelligence are time. I wonder if that's supposed to be many tests that's purpose? I've never heard that word. Have you guys? Purport? What does that mean? I don't know. I feel like it makes more sense. That's purpose to measure intelligence.
I think that's perfect. Yeah.
I don't know. Okay, anyways. Good thing I'm not an English teacher. I'm also really bad at spelling. The decision of how much time to allow for such a test often is made after examinations of samples of times for completion of practice versions of the test. Below is a histogram summarizing 48 such times for completion for one test. Based on the histogram, estimate the standard deviation of the sample of 48 times. So obviously, we're not going to take each data entry 48 times and like add them all together. And to be honest, we don't know the actual data. All we know is that between the interval of 8 to 12 minutes, there was 6 people who finished in that time. So that's the weird thing about histograms is we don't actually know the real data. We don't know their numbers. It could have been 8.5 minutes or it could have been 11.5 minutes. We just know that 6 of them were in that interval, right? That's how we read this histogram. And similar between 12 and 16, there was 15 of them. So here's the quicker way to basically calculate the standard deviation of a histogram. You guys know how to find the mean of a histogram, right? We've done that. I think that was on the last lesson. So we are talking about a sample, right? Yep, sample of times. Oop. Sample. So for mean, I'm going to use this notation. Okay. So we have to use our midpoints to calculate the, basically like, there's 6 entries and we don't know exactly where they were, so we use the midpoint to approximate it. So like the midpoint here would be 10. In this first interval. So we use the midpoint just to approximate the mean here. So there's 6 that were within, 8 to 12, so we say 10. And then move on to our next one. There's 15 that are in between 12 and 16, so we'll go midpoint of 14. Bless you. Okay. And obviously, guys, this is like equivalent to using the midpoint and doing 10 plus 10 plus 10 6 times. And then, okay, now we have 15. That is approximately 14 plus 14 plus 14, etc. All right, next one. 24. Midpoint is 18. Oh, gosh. I thought that was our bell. That scared me. It's like they went by so fast. 3. Okay. So to find our mean, there were 48 of these. So similarly, I would calculate probably my top, divide that by 44. I got 16 was the mean. And if I draw that in here, that looks like it could probably be about the average because I had, a little bit more in that 8 to 12 range. That's kind of close, not as close to the mean, but then only 3 on the other hand side. So that number makes sense. All right, so now to calculate the variance, similar to the math we had to do here, where we had to multiply each entry by 6, because there were 6 entries in that interval, we'll have to multiply the deviation also by 6. So I'm calculating how far 10, the midpoint, deviates from the mean, and there's 6 of them that do this, so we'll times this by 6. It's still squared. Okay, does that make sense? So we're still doing like the sum of all deviations. I just have to times this by 6 because there are, instead of doing it 48 times, there's 6 that are within this interval. Yes.
So it's supposed to be 16.
Yes. Sorry. Thank you. 16. Good catch. All right, next one. 14 as my midpoint. How far does that deviate from my mean? I have to square it, and then I do have to times this by, there's 15 of those. 15. That's kind of how I think of it. And I think, okay, So same calculations here. Now I'm going to figure out how far is 18 using my midpoint. So I don't know the exact data. How far does that deviate from my mean? And how many do I have there? Whoa, 24 of those. All right, last one. 3 minus 16. Oh, sorry, not 3, 22. Oof, you almost put that in the wrong spot. How far does 22 deviate from our mean? And we have 3 of those. All right, I'm not going to divide this by 48. I'm going to divide it by 48 minus 1 because it's talking about a population. All right, up top, when I did all that math, I got 480. So I have 480 divided by 47. So last step here to actually calculate the standard deviation, we just square root that number. I got 3.2. So if we kind of looked at 3.2, so our mean is 16. So 3.2 would just be below 20. So it's kind of saying on average, this is about where those data entries are located, which again kind of makes sense because we have some on the high end, some on the low end, but that's what that kind of means. Like on average, that's how far away from the mean our entries are. Okay, what do we have next? Oh, have you guys ever heard of a bell-shaped curve? Normal distribution at all? So it's basically like any data that's symmetrical like this, and if you were to kind of like trace it, here's obviously like a histogram, but if you were to kind of trace it, it has this like bell-shaped curve to it. It's also called like a normal curve, and there's like just some special relationships with like standard deviation that can be applied to the normal distribution. And it shows up kind of like a lot in real life. And then after this, I don't know if we'll probably get to it today, we do learn kind of a rule that like if it's not a nice normal bell curve, how can we calculate some of these like statistics, I guess. Let's start with the normal one and then that'll make more sense. Okay, so that's basically just all a normal distribution is. It's something where the data is symmetrical, and if you were to kind of trace it, it has this bell-shaped curve. So here's this really important empirical rule. So this only applies to normal curves. So like I said, we do kind of have a rule for ones that don't.
This is what we did.
Is this what you did at AP Psych? So it basically just says that wherever your mean is, within all data, no matter what the numbers, as long as they have this type of distribution, that 68% of the data is going to lie within one standard deviation away from the mean on both sides. And that within 2 standard deviations, 95% of your data will lie within there. So a really common one is like IQ scores, like truly IQ scores, like have this bell-shaped curve. So like 68% of people, I shouldn't say it. Well, I guess you could think of that way, lie within whatever the standard deviation is. Let's say it's, I don't know, 10 is the standard deviation. So they lie 10 higher, 10 lower than the average IQ. That's 68% of the people would lie within that. 95% lie within 2 standard deviations, and 99.7% of our data lie within 3 standard deviations. So that's basically what the empirical rule is. The only thing I'd maybe jot down here in your notes is these symbols, what they're showing you. Like this symbol is showing you the mean. That's what that X bar, the mean, minus 3, and then S, that's our standard deviation. Okay. And then this, obviously, the center right here, that's your mean. That's our middle. Okay, so we're just going to try it. Let's see, I have a problem about this. All right, Chow is human resources manager for 2 hospitals in a metropolitan area. He's comparing data about the amount of sick leave in days, taken by each of 68 full-time nurses in each of the 2 hospitals. The histograms below show the distributions of the 2 data sets. Each histogram shows the number of days of sick leave taken on the horizontal axis and the number of full-time nurses on the vertical axis. The means and standard deviations for the data set are given to you. All right, here's hospital A. The mean is 6.3. Standard deviation is 2.2. You can calculate standard deviation with any data set. That's numerical, I should say. This only applies to symmetrical data. That percent of your data lies within those standard deviations. Hospital B, the mean is 5, and the standard deviation is 1.4 days. All right, question A says, identify the data set for which it would be appropriate to use the empirical rule. What do you think, A or B? B, why?
Is it, bell-shaped normal?
Exactly. Yep, exactly. It has that bell-shaped curve. It has a normal distribution. How do we describe this distribution?
Skew left.
Skew left. Good. Okay, so this one is B. Okay, so now we're going to actually apply the empirical rule to make the following approximations. I'm going to keep my chart up here and I'll just kind of read the questions. The percentage of amounts of sick leave between 0.8 days and 9.2 days is approximately how many percent? All right, so we know, I'm going to look at my graph here. We know the standard deviation is 1.4 and my mean is 5. So looking at my x-axis here, 5 would be right down the middle. There's my mean. So if my standard deviation is 1.4, we can basically essentially calculate, okay, how far is one standard deviation by starting at 5 there, adding on 1.4, adding on another 1.4 would be 2 standard deviations away, 3 standard deviations away, etc., etc. So I don't really know how to show my work here. I guess I can do this. 5 plus 1.4, that'd give me 6.4, so I'm just going to kind of jot it right here. That's 1 standard deviation to the right. Let's go 1 standard deviation to the left. So minus that 1.4, that'd give me 3.6, which would be about here. Okay, so there is my data. If I were to, I wouldn't do this, but just look up here for a second. If I were to look here, according to the empirical rule, 68% of my data is going to lie between 3.6 and 6.4 hours. Okay, that's not what they asked me. They want to know between 0.8 days and 9.2 days. So we're going to have to keep going here. So if I move out another standard deviation on each side, put this one in red. So I'll go 6.4 plus another standard deviation is 7.8. So now this is 2 standard deviations away from my mean. Now let's go on the other side. So 3.6 minus another standard deviation, 2.2. Okay. I still haven't got out to that 0.8 to 9.2 range yet, but just to apply the empirical rule, this says 95% of your data is going to lie within this range now, within 2 standard deviations. All right, we just got to go one more. One more out, because you'll see 7.8 plus another standard deviation would get me to that 9.2. And 2.2 minus 1.4 would get me to that 0.8. Okay, so what we basically figured out there was this range was within 3 standard deviations. So according to our empirical rule, what percent of our data is going to lie within 3 standard deviations? 99.7%. And again, this applies. Oh my gosh, my picture's always moved. This applies to all normal distribution. So it doesn't matter what the numbers are. According to this rule, it's going to be approximately 99.7%. Okay, so C, which I kind of already talked about this, approximately 68% of the amounts of sick leave are between which days? Yep, 68% is within 1 standard deviation. So within 1 standard deviation, we'll do those blue numbers, 3.6. And 6.4 days. Okay. This is probably actually a good stopping point. We'll just talk about Chevy Chevs. Have you guys talked about this? Chevy Chevs? This is basically just like, how can we figure out what percent of our data is within the standard deviations if it's not a bell-shaped curve? So we'll save that for tomorrow, and then I'll give you guys the rest of class to work on your Alex. Chevy Chevs.